Hello. Up until this point, with taking derivatives, we've dealt only with functions where, we can write, that y on some graph is equal to f of x, some function of x. And we're dealing with a graph like, pretty standard, where we just have, our y is equal to f of x up here, our x axis, and then we have, some curve. And we've been finding the function of that curve at specific points and generally. But what we haven't dealt with yet is what happens when you have something like a curve like that isn't a function. But you can still see that there is a slope. There are tangent lines on this curve. They just aren't represented in the same way. And you might say, well, just replace your variables and define the derivative differently. And that's part of it, but what if we're dealing with a curve like this? What if we're dealing with a circle? In this video, we're going to find the derivative, or the slope of the tangent line, on some point of a circle. And to do this, I'm going to bring up something called implicit differentiation. And this is a form of taking derivatives where you can't really do the traditional thing where you have y as a function of f of x, and you find dy dx or df dx or whatever you're calling it. Instead, you have something like our circle, and what's the equation of a circle? The equation of a circle is that x squared plus y squared is equal to r squared, where r is our radius. What happens if we want to find the derivative of y with respect to x? It's not f prime of x because this isn't a function. So what is this going to be equal to? Well, there are a couple ways you can approach this. For one, you can say, well, let's put y as a function of x. And of course, we can do that as long as we make two separate functions. We can kind of cut the circle in half and say that this upper part is, well, let's see, we can rearrange this. Y squared is equal to r squared minus x squared, or y is equal to the plus or minus square root of r squared minus x squared, right? And so we have some function, y1 is the square root of r squared minus x squared, and then y2 is the negative square root of r squared minus x squared. And those would define these two halves here, right? This would be y2, and this would be y1. But there's sort of a better way to do that, because at that point, you have one formula for the derivative for only half of the curve that you're mentioning, and another one for the other half, and it gets kind of confusing. And so there's another way you can do things, and I'm going to erase this. Here we go. There's another way of doing it, and I personally really like implicit differentiation because, it starts to be kind of evocative of differential equations because of the operations you do and how it relates more to, it's more related to equations than just an operator like we've been doing before. Essentially what you do is you just take the derivative of both sides of the equation, right? You can do that. They're both equal. So we just take the derivative of both sides and they'll stay equal. So what happens when we do that? We take the derivative with respect to x of x squared plus y squared. What are we doing? This is so weird. Is equal to the derivative with respect to x of r squared. Okay, well, the derivative with respect to r squared, that's just going to be 0, right? There's no x in there. That's just a constant. So we have that 0 is equal to the derivative with respect to x of x squared plus the derivative with respect to x of y squared. So the first part's pretty easy. What's the derivative with respect to x of x squared? You know, x squared, if we just have some function x squared, the derivative of that function would be 2x. So 2x plus, well, what's the derivative with respect to x of y squared? And this is the really interesting part. So if we're taking, and this brings us back to the chain rule, if we're taking the derivative with respect to x of y squared, that's really just the same as having two functions, one inner function and one outer function. You could say that our outer function is x squared, but then our inner function is y, which is kind of a weird idea, where we have y squared. Because y is inside of it, it's a little weird, but this is how we can break it up into inner and outer functions. Or if you prefer, you could say, where we just make y is equal to u, but not getting into all of that, the way that you do things with the chain rule is you take the derivative of the outer function, no matter what it is, with respect to the inner function. So we can just pretend that y is x or whatever, and that's just going to be 2 times, it's the derivative of that outer function, whatever's inside squared, but we have to keep the thing that's inside. So this is going to be 2y, the derivative with respect to x of y squared, but we're not done because we have to multiply by the derivative of the inner function with respect to x. So all we've done is take the derivative of this here, plug y in for x, and now we're taking the derivative of this and multiplying it. So what's the derivative of y? Well, that's dy dx. If we're trying to make y as having some relationship to x, and we want to find dy dx, right? That's what we're searching for in the first place. Here it is, right here in our equation. So that's kind of interesting. So if we plug this in, and I hope you really understand where this comes from, that we are taking, what we're doing when we're taking the derivative with respect to x of y squared is we're just breaking it down into an outer and inner function, right? It doesn't matter what that y is when we have y squared, as long as we plug it in and multiply by the derivative with respect to what x of y in the first place, right? Y could be, 2x plus 1, and if we're taking the derivative with respect to x of 2x plus 1 squared, we still take the derivative of x squared, plug in 2x plus 1, and then multiply by the derivative of the inside, which would be 2. Essentially, the thing that we're squaring there, we're just saying is y. And we want to find this relationship between y and x. dy dx, that's going to be the slope at any point. Yeah, maybe the relationship between y and x is not clear, but that's going to be the slope at any point along this circle. So, like a tangent line. So we have 2x plus 2y times dy dx. All we've done is done the chain rule. We've taken the derivative of the outside, plugged in y, and then took the derivative of the inside, which is y. I think that should be pretty clear. So we can switch this around now. We can say that 2y times dy dx is equal to negative 2x. I'm just subtracting 2x from both sides, and then I'm going to divide both sides by 2y. There we go. And we get that the derivative of y with respect to x is equal to negative 2x over 2y. Or those 2's can cancel out, and we just get, let's try to get those 2's to cancel out. We just get negative x over y. So this is a new kind of derivative, because what we've done is we haven't had taken the derivative of some function f of x and just had an answer that's in terms of x. This time we have an answer that depends on both the x coordinate and the y coordinate. So if you have an x coordinate and y coordinate on your circle, you can plug those in and find the slope at that point on the circle. And we've done that just by taking the derivative of both sides, which is something called implicit differentiation. And this is very useful when you're taking the derivatives of curves, or the slopes of tangent lines on curves that do not fit the function definition. We're going to be going into more examples in the next videos, and since this is kind of a new concept, if it's not clear now, hopefully I can make it clear in the coming videos. Thanks for watching.